This is part 6 of the tutorial on the church encoding, and here I will talk about how to encode dependent pairs and some types that are based on dependent pairs, which are refinement types and singleton types, as well as evidence for type class laws. So what is a dependent pair? It is a special kind of type that is usually not available in programming languages that people normally use. It's a dependent type in the sense that it contains two values. The first value is of some type x. That could be natural, say, or text or something else. And the second value has type that depends on the first value. It is not a type that depends on the type x. It is the value, the little lowercase x, on which the type of the second value depends. Now, this is a very unusual situation for ordinary programming languages. So p here is a function from the type x to the kind of types. So in other words, px is some other type. As an example, if this x is natural, then this could be a function that for each natural number gives a different type that depends on that natural number. For example, the type of arrays of length n, where n is that first natural number. That is not available in Dhall built-in, but it can be encoded in Dhall using a technique similar to the church encoding, where we first look at how we could encode pairs in church encoding. That I already talked about in a previous tutorial. But essentially this is the type that you would write down in order to encode a pair of types A and B using the church encoding. So this type is strictly equivalent to the type of pairs AB. Now, because this is curried, the type of the second curried argument could depend on the first curried argument, and in Dhall it is allowed that the type depends on the value of the argument, not only on the type. So this is the dependent type in other words. And so in this way we can encode the dependent pair. We write down the church encoding of a pair, but we change, instead of just two different types, A and B, or X and Y could be here, we say, well, let's denote by lowercase x the value of the type x, and then let's say the type of the second curried argument must depend on that value. Now, what kind of values that are going to be, I'm going to show on some examples. So this allows us to define in Dhall a general type, that is the church encoding of arbitrary dependent pair. So dependent pair for x being a type, and for a function from x to type, that gives us a new type that is going to be the dependent pair of xp. And so that is a definition. We just put lambdas in front of the church encoding. So with the power of Dhall, that allows us to have arbitrary parameters, arbitrary type parameters, and arbitrary dependencies, we can encode dependent pairs. Now, up front, I should say, Dhall was not designed for working with dependent types. This is perhaps an accident of the implementation of Dhall, that it is so general that it accepts when the type here depends on a value and not on a type. But let's see how we can use that. So first, how would you create a value of this type? So to create a value of this type, you need to specify type X, then a value of that type. Then you need to specify this constructor, which is a dependent type from X to type. And then you need to specify a value of that type dependent on X. And then once you have given this data, the function will create for you the dependent pair. How would it do that? It will be just encoding the church encoding. K is the kind of a continuation, and then you just apply that continuation to the given arguments. So a theoretical point is that functions from a dependent pair to some other type are equivalent to a simpler type like this. So this is similar to what happened for existential types, where functions from existential type can be simplified. So let us now look at the at how to work with the dependent pair. So first thing we might want to do is to extract data from it. So it's a pair, right? So you think, I want to extract the first part of it and I want to extract the second part of it. Well, so extracting the first part can be done pretty straightforwardly. You take an X, you take a P, you take a dependent pair XP, and you can extract X by applying the continuation. So this dp is applied with X, and the continuation just ignores the px argument and returns X. And so this is really relatively simple. However, the second part cannot be extracted in Dhall so easily because of the typing, because the type of that depends on the value that is inside the dependent pair, and you don't see that value when you write down the type signature. So it will be very difficult to write it. Maybe you need to first extract the first part of the dependent pair, which will give you this little x, and then you can say what the output type is of the second part of the pair. But Dhall cannot type check that if you write it down. So you would need a more powerful language if you wanted to work with that. But practically speaking, what you want from dependent pairs is to encode things like refinement types. So for that it is much easier, and you don't need the full power of dependent type languages. So what is a refinement type? So we take some parent type, so to speak, let's say natural, and we want to say that we consider natural numbers that satisfy a certain condition, and that we want to say that's a new type, which usually is called refinement type. So it's kind of a refinement on the natural numbers. It's a subset of natural numbers. So for example, let's say natural numbers not greater than 10. So what do you do that? How do you do that? Well, what you want really is you want a pair of a natural number and an evidence that that natural number is not greater than 10. What is the type of that evidence? For example, we can encode that evidence using the type 0 equals 0, the dependent equality type, which is built in Dhall. If x is greater than or equal to 10, then this function returns 0. And then this type will be inhabited, and so this will be evidence that x is not greater than 0. So therefore, let's take p as a function that takes x and returns this type. So the first step is to define this function, which is the predicate. And the predicate is from natural numbers to type. And now that type is going to be this. And this type is going to be void, that is no values, when x is 10 or greater, is 10 or greater. So this is a natural less equal than 10. It is going to be void when x is greater than 10, because then subtracting 10 from x will give you a number like 1 or 2, and that's not going to be equal to 0. And so that will be void when x is greater than 10. But when it's equal to 10, then it's not void. So let me perhaps correct what I said before. So this is then how we define the dependent pair with natural and this predicate. And that is the type, that is the refinement type for naturals not greater than 10. How do you define values of this type? Well, you define a function that takes a number and prepares the evidence that it is not greater than 10. And that's this function, make natural less than equal 10. And all you need to do is to put assert in there. To assert that the predicate holds for this number. So you see, when you define this number in Dhall, you have to repeat it. So you write 8 here, and you also write 8 here. Now you could refactor this to say let here, you say let n equals 8 in make natural is equal 10 and assert this n. But this n must be assigned in the scope of this expression. So you could not make a function that takes an arbitrary x and returns this. Because the type checking is eager and occurs before evaluation. And so you cannot refactor this into a function. You have to repeat this 8, or you have to repeat something else if you refactor inside this expression. So this is a bit difficult, but there is a way of reducing the code duplication and to making this easier to work with. And one way is to say, well, actually, this type is not a function, is a function of 8, technically speaking, but when this type is inhabited, then it's going to be always the same. It's going to be the type 0 equals 0. So then let's write that evidence once and for all, and then this will be shorter to write. You don't have to say make natural 8 and then again 8 somewhere. And we can make it even shorter when you say, well, you make a function predicate that gives you a unit type when x is less or equal to 10, and a void type when x is greater than 10. So that's just, let's define a type like this. Well, you can do this in Dhall, right? So identifiers can be anything if they're in backticks. So then, if it is less than 10, then it's a unit type, and otherwise it's a void type. So then, this is even easier to use, because then you just put this symbol, which is the value of the unit type in Dhall, and you're done. So in this way, you can work with refined types and refinement types. And the function that takes the first value out of the dependent pair can be used to extract the bare natural value of a parent type from the refinement type. So here I want to make a comment that in Dhall, certain conditions cannot be expressed at runtime. They can only be asserted at compile time. And one example is that strings are non-empty, say, and that you can assert at compile time like this. You can assert that the string is empty, and then you can assert that the string is not empty. I explained here how. It's a bit of a trick, but essentially it's a text replace function that you use in a certain way, and then when the string is non-empty, then the replacement replaces, and when the string is empty, then it does nothing. So then in this way you can assert that the strings are not empty. In any case, the refinement type doesn't need having a function that evaluates the condition. It is sufficient that you can present some kind of evidence, and evidence can be just an assert value. And so here's an example where, using the library by Dhall, which is this library, Dhall text utils, in here, which I'm just mirroring on my website. Then you can write code like this, where you have string is valid, it is starts with A or Z, or it's alphanumeric, and so on. So you can have different conditions, but all these conditions are actually evaluated at type checking time, because Dhall does not allow you to perform text manipulation. And so here you would create a value that this is a valid string, and X is a refinement type that takes a string and validates the string at compile time. So this only works with literal values, or values that are literal at top level. And another example of using dependent pairs is a singleton type, which is a very simple example of a refinement type where the condition is just that the value is fixed. So it's a value, say, with parent type text, and the value is this. So that's the type. So if you say something has this type, then you know it's really text, and it's equal to ABC. And so you can encode this using dependent pairs. I show this here, but actually the ergonomics is not great. And so if you want to have a function whose argument has a singleton type, then actually the type signature of that function will need to include the value of that type. And so here's how you would call that function. And the problem, of course, is that no, this is the single X, is that it's not very helpful. If you already know the fixed value, you don't need to pass it as an argument to a function. So in any case, singleton types can be encoded, but they don't really give a lot of practical advantages in Dhall. Refinement types may give advantages if perhaps better syntax can be defined for them, but in any case you can encode them in Dhall, and syntax can always be defined as syntactic sugar, that is standing for encoding that already exists in the language. That's a safe way of extending the language. You add new syntax sugar that desugars into something that can already be encoded in the language, but just more verbosely. So finally, what I'm going to talk about in this tutorial is how to present evidence for type class laws. Here's an example. We have a semigroup, and the type class contains a simple single function combining two values into a new value. for this new semigroup operation. And the law is the associativity law. And so we can write down the type of that law, which is that associativity should hold for arbitrary values x, y, z of the semigroup type. And then you can define a type of lawful semigroup, which is a dependent pair of having that T has an evidence of semigroup, but also the law holds for that evidence, because that evidence is the append function, and so the law should hold for that function. And so in this way, you can produce evidence at the same time as you're defining a type class evidence. You produce evidence that the law holds. So I'm illustrating this with an example of this type, which is a semigroup, using function composition as the operation. And I'm using this example because Dhall's typechecker can verify that the laws hold for this. It's simple enough that it can verify that, because the typechecker right now in Dhall is not powerful enough to verify laws in many cases, but in some cases it is. And so this is just a kind of an illustrative example showing that you can define a type class together with its laws and using the dependent pair. And so then if you have presented a value of this type, then you have presented at once the implementation of the type class methods and an evidence that the laws hold for those methods. So at this point, I am finishing my series of tutorials on the church encoding. I have shown that church encodings can be used to encode lots of types, from simple types like pairs and unions, to recursive types, to type constructors, recursive type constructors, nested recursive types, GADTs, hierarchy types of other kinds, existential types, and even dependent pairs, which is an advanced kind of application. But actually, for Dhall as a configuration language, it would have been very useful to have better syntax for dependent pairs, because then you could encode certain constraints on your configuration, saying that, for example, certain strings must be alphanumeric or no longer than 10 characters or something like that. Or some numbers are not bigger or not less or something than something else. And if you could encode these types more easily in Dhall, more easily than what I just shown, because you can encode them in this way, but it's then going to be quite verbose, and you would have to explicitly extract the parent type values from refinement type values. So if you are preparing, say, a JSON output, then you cannot directly export this complicated higher order function into a value. And so it will be a lot of code to do that in Dhall. So, but with better syntax, maybe in a future version, this would work. So it just shows that Dhall is already powerful enough to encode all these constructions without any changes in the language. And just the syntactic sugar might be necessary to make it practical to work with those types. This concludes the tutorial.